Hello everyone. In the first part of the metallurgical operations, we have already discussed crushing and grinding of ore and concentration, where the unwanted earthy and siliceous impurities were removed. The third step of this metallurgical operations is conversion of the concentrated ore into metal oxide. Since many metals can be easily obtained from their respective oxides by reduction, therefore the extraction of metal actually involves two chemical processes: conversion of ore into metal oxide and reduction or electronation of the metal oxide into free metal. Here we'll study the conversion of ore into metal oxide. Metals are usually present in ores as hydrated oxides, carbonates, and sulfides. Depending upon the nature of the minerals present in the ore, roasting and calcination are used for conversion of ore into their respective oxides. Calcination. Calcination is the process of converting an ore into its oxide by heating it strongly below its melting point, either in absence or limited supply of air. This process is commonly used to convert metal carbonate and hydroxide to their respective oxides. During the process of calcination, moisture is driven out, volatile impurities of sulfur, arsenic, and phosphorus are removed as their volatile oxides. Water is removed from the hydrated oxides and hydroxide ores, and the carbonate ores are converted into their respective oxides by the loss of carbon dioxide. As you can see here in the reactions, limestone, dolomite, malachite, calamine, these are the carbonate ores which are heated strongly to convert into their respective metal oxides. Bauxite and limonite are heated in absence of oxygen or air to convert into their oxides, where the water is removed from their hydrated oxides. Calcination makes the ore porous and hence easily workable in subsequent changes. It is usually carried out in a reverberatory furnace. Roasting. Roasting is the process of converting an ore into its metallic oxide by strongly heating it at the temperature insufficient to melt in excess of air. This process is commonly used for sulfide ores. The following changes occur during roasting. The moisture is removed, organic matter is destroyed, the non-metallic impurities like that of sulfur, phosphorus, and arsenic are oxidized and are removed as volatile gases. As you can see in the reactions given, sulfur is converted to sulfur dioxide, phosphorus to phosphorus pentoxide, arsenic to arsenous oxide, and the sulfide ores are converted to their metallic oxides. The sulfur dioxide produced during this process is used for the manufacture of sulfuric acid. Roasting also makes the ore porous and easily workable in subsequent stages. Like calcination and roasting, these both processes can be carried out in a reverberatory furnace. It's a kind of a furnace in which fuel does not come in contact with the charge. The flames are directed from the roof of the furnace onto the charge, and air supply is controlled by the vents. During roasting, air vents are kept open, while during calcination, air vents are either partially or completely closed. Now, there comes three important terms which you need to know. One is gangue, second is flux, and third is slag. What is gangue? The earthy waste substances or the impurities present in metallic ore. These are collectively called as gangue or matrix. If the calcinated or the roasted ore still contains non-fusible impurities of earthy matter An additional substance called flux is added during the reduction process. Thus, flux is a substance that chemically combines with the gangue, which may still be present in the roasted or the calcinated ore, to form an easily fusible material called slag. You can say flux combines with gangue to form slag. The slag thus formed melts at the temperature of the furnace. It is insoluble in the molten metal, and also being lighter floats over the surface of the molten metal, from where it can be skimmed off from time to time. Types of fluxes. Depending on the nature of the impurities present in the ore, fluxes are classified into two types: acidic fluxes and basic fluxes. For basic impurities like lime or metallic oxides of calcium oxide or ferric oxides present in the ores, acidic fluxes like silica or borax are used. For acidic impurities like silica and phosphorus pentoxide, etc., present in the ore, basic fluxes like limestone, magnesite, or hematite are used. Thermodynamic principles in extraction of metals. It is observed that some metals are easily reduced. Reduction occurs at room temperature, but others are reduced with difficulty. That means the reduction occurs at high temperature. Now, to predict which element will be the most suitable reducing agent for a given metal oxide and what would be the optimum temperature at which reduction will proceed smoothly, the basic concept of thermodynamics is quite useful. For any process, the Gibbs free energy change is given by the equation delta G is equal to delta H minus T delta S, where delta H is the enthalpy change, delta S is the entropy change, and T is the absolute temperature. If delta G is negative, this means the reaction will proceed towards forward direction, forming the product. The criteria of feasibility of a reaction at any temperature is that the delta G of the reaction must be negative. So if delta S is positive, on increasing the temperature, T delta S will increase. And when T delta S is more than delta H, delta G will be negative and the reaction will proceed in the direction towards product. Second, a reaction with delta G positive still can be made to occur by coupling it with another reaction having larger negative delta G. So the net delta G of the two reactions is negative. Such coupling reaction can be understood in the terms of Ellingham diagram, which plots standard free energy of the formation of oxides per mole of oxygen as a function of absolute temperature. Ellingham diagram. It normally consists of the plots of delta G versus temperature for the formation of oxides of elements. The same diagrams can also be constructed for the sulfides and halides of these elements. Ellingham diagram helps in the prediction of feasibility of thermal reaction of an ore. In the conversion of a metal to metal oxide where it reacts with oxygen gas, this is quite helpful. In the reaction, oxygen gas has been used up and metal oxide as a solid is formed. Since gases have higher entropy than liquids and solids, therefore during this reaction delta S becomes negative. Thus, if the temperature is increased, T delta S becomes more and more negative. In other words, delta G increases with increase in temperature. Normally, delta G decreases with decrease in temperature. Or you can say, Gibbs free energy of formation of oxides versus temperature line have positive slope for most of the reactions involving the formation of metal oxides, as you can see in this figure. Each plot is a straight line except when some change in phases takes place, like from solid to liquid or liquid to gas. The temperature at which such a change occurs is indicated by an increase in the slope on the positive side. For example, in the zinc to zinc oxide plot at the boiling point of zinc, there is an abrupt increase in the positive slope of the curve. Similarly, in the positive slope of magnesium to magnesium oxide curve increases abruptly at the boiling point of magnesium. The small circles here or the small dots here indicate the melting point and boiling points of the metals. Here are certain characteristics of the diagram. As I have already told there in the ellingham diagram explanation, all the plots slope towards up since delta G becomes more positive when temperature increases, that is stability of the oxides decreases. Second, a metal will reduce the oxide of other metals which lie above in the ellingham diagram. That is, the metals for which the free energy of formation of their oxides is more negative can reduce those metal oxides which have less negative delta G. That is free energy of formation. The decreasing order of the negative values of free energy of formation of the metal oxides is given here. From here you can see that aluminium can reduce ferrous oxide, chromium oxide, nickel oxide in thermite reaction, but it will not reduce magnesium oxide at the temperature below 1773 Kelvin. Without going into calculation for Gibbs free energy, we can still predict the feasibility of a reduction process simply by looking at the ellingham diagram. Metals for which the free energy of formation of their oxides is more negative can reduce those metals for which the free energy of formation of their respective oxides is less negative. In other words, at any given temperature, any element will reduce the oxides of other metal which lie above in the ellingham diagram because of the free energy change for the combined redox reaction will be negative by an amount equal to the difference between the free energy of formation of the two oxides at that temperature. Further, greater the differences, easier is the reduction. We come back again to the ellingham diagram, and from here we can easily predict that magnesium can reduce aluminium oxide, zinc oxide, ferrous oxide and cuprous oxide more readily than aluminium can reduce zinc oxide, ferrous oxide and cuprous oxide. Similarly, aluminium can reduce zinc, ferrous or cuprous oxides more readily than zinc reduces ferrous oxide and cuprous. So here you can say if you compare the reducing agents that will go from magnesium to aluminium to zinc to iron, and least will be for copper. However, in case of less reactive metals like silver and mercury, the free energy change of formation of oxides becomes positive at higher temperature. This suggests that silver oxide and mercury oxide, Ag2O and HgO, are unstable and they decompose at higher temperature, liberating the corresponding metal. So this was all for second part of the metallurgical process. In the third part of the metallurgical operation, we'll study about the fourth and the very important step, that is the reduction and electronation of metal oxides into metal.